Hello everyone, welcome to Civil Engineering and Stuff. And in today's video lecture, we are going to do a numerical on Candy's theory for the design of regime channel. Now, the theoretical part and the conceptual part we have already discussed in the previous lecture. So, if you haven't watched that video, it is highly recommended to watch that video first before we dive into the numerical. And before we start with the numerical, it is highly recommended that you carry a notebook, calculator, and the design steps with you so that as we move along, I'll request you to solve the numerical in the calculator as we move ahead. Okay, but merely watching this video won't be of much help. So I hope you are carrying and following this instruction. So let's move towards the numerical. The question that we have in front of us today is that we have to design an irrigation channel to carry a 50 cubic of discharge. The channel is to be laid at a slope of 1 in 4,000. The critical velocity ratio is 1.1 and we have to use cutter's rugosity coefficient that is given to us as 0.023. So we have to design a regime channel based upon Kennedy's theory for the design of regime channel. So first of all, let us write out the given parameter that is given to us. We have been given a discharge of 50 cubic. We have been given a discharge of 50 cubic. The bed slope is given to us as 1 by 4,000. The critical velocity ratio M is given to us 1.1 and cutter's rugosity coefficient is given as 0.023. These are the given parameters. So let's design the channel, design a regime channel. So the first step, the first step in the design of regime channel as per Kennedy's theory was to assume a to assume to assume a trial depth. We have to assume a depth of flow of water, and in this case we are going to assume the depth to be 2 meters. You can assume any depth you want. For the sake of discussion here, we are going to assume as 2 meter. Now, in the previous lecture, we have discussed certain guidelines, and if you look into the guidelines for a discharge of 40 to 80 cubic, the trial depth you can assume as 2.5 meter just for the starting point. But we are assuming 2 meters just for the sake of discussion, so as to increase that. What will happen if at this depth we do not get the value? Okay, so on and all, you can assume anything you want. So the first step is that we have to assume a trial depth, and we have assumed a trial depth of 2 meter. After assuming a trial depth of 2 meter, we have to find out the critical velocity V naught. And V naught is we have to find using the formula given by Mr. Kennedy as 0.55 m y to the power 0.64. M is the critical velocity ratio, y is the trial depth that we have assumed. So V naught is equals to 0.55, 0.55, 1.1. We have been given in the question. The critical velocity ratio is 1.1. Depth we have assumed as 2, so it will be 2 to the power 0.64. All right. So if we if we solve this value, it will come out to be 0.942 meter per second. 942 meter per second. I hope this is the same value that you are getting in the calculator as you're solving along. So we have completed this step one. Then we are going to do the step two. Then we are going to move to the step two. What was the step two that we had discussed in the previous lecture? The step two was that we have to find out the area. And to find out the area, we are going to use the formula A equals to Q by V naught. Let's do that. The second step is to find out the area. To find out the area. Area A is equals to Q by V naught. V naught we have found in the step 1. Q is already given in the question as 50. V naught is 0.942. So upon solving, the value will come out to be 53.1 meter square. So the area that has come out is 53.1 meter square. So this marks the end of step 2. Now what is step 3? After completing step 2, we are going to move to the step 3. And step 3 is, in the step 3, what we have to do is we have to find out the width as well as the parameter. And to do so, first of all, we have to assume that we are designing a trapezoidal channel section. So, assuming a trapezoidal channel section, assuming a trapezoidal channel section, Now this channel section has a side slope, which again we have to assume with side slope of half horizontal is to 1 vertical, right? This is assumed in the ratio of in this form, and horizontal is to 1 vertical. We have discussed about this in the previous video. Okay, so we are not going to go into detail. Okay, so we have assumed that we are designing a trapezoidal channel section, and since we are assuming it as a trapezoidal channel section and the side slopes are not given to us, we are going to assume this side slope also. Okay, so this is the value. Now, so we have to find out the area of this trapezoidal channel section in which the water is flowing. The water is flowing at a depth y. This y in the first tile we have assumed to be how much? 2 meter, and has a width b. This has a side slope of half horizontal is to 1 vertical. Correct? So what is the area? What is the area of a trapezoidal channel section? Now, if we talk about the formula, the area is given by b plus ny into y. Okay, but if you find it very difficult to remember this area, the formula for the area, then you can find out the area by dividing the trapezoidal section into different sections, and then the area you can find area of rectangular section, area of rectangle. If you see here, you have this section as rectangle plus twice of area of triangle, and you can see here we have triangle. This is first triangle, this is second triangle. Okay, just in case if you find it difficult to remember this formula, you can use this expression also. Okay, so area of this trapezoidal channel section, area of rectangle is b into y, b into y plus twice of half. Base is, this is the base of the triangle, this is the triangle, right? This is the triangle, so this is the base. So the base will be, if the this will be ny. All right, so we have ny into depth or height y. Okay, so this is the another way by which you can find out the area. All right, so the area is equals to b plus ny into y. Width, what is the width given to us? We don't know. What is the area? We have found out in step 1. Area is 53.1. So we have 53.1. 53.1 is equals to b, that is the width, into n is half, into y we have assumed to be 2 meter into 2. Okay, so through this we will find out the width. The width will come out to be how much? Solve it and just see if I'm getting the right value. B is will come out to be 25.55 meter. Likewise, we have to find out the parameter. What is the formula for parameter? B plus 2y under root 1 plus n square. How did we get this formula? You can see in the figure here, you can see this is the b, right? This is the b, and this is the side slope. The formula for side slope, it is under root n square plus 1. Correct? It is under root n square plus 1 up to the depth of y. Okay, so we have two side slope, that's why into 2. So 2y under root 1 plus n square. So p parameter is equals to b is 25.55 plus 2 depth, again the trial depth that we have assumed in the step 1 plus n square. The side slope we have assumed, that is half. So solving this, the value of p will come out to be 30.03. Unit will be meters. Very important to remember the units. Okay, so this is through this we have completed our step 3. Okay, if we just revise and look into this, you can see here that we have find out the width as well as the parameter. So our step 3 is complete. Now we move to the step 4, and step 4 is to find out the hydraulic mean depth using formula R equals to A by P, and after that using Cutter's equation we will find out the actual velocity. Okay, so we have step 4. Now we have step 4, and step 4 is to find out the hydraulic mean depth R, which is equals to A by P. Area already found in the previous steps. Area is 53.1 meter square. Let's put here 53.1. Parameter is 30.03. Parameter is 30.03. 30.03. So the hydraulic mean depth will come out to be 1.77 meters. R comes out to be 1.77 meters. So we have completed our step 4. Now in step 5, we have to find out the actual velocity. We have to find out the actual velocity v, and we are going to use Cutter's equation. So for this v will be equals to the Cutter's coefficient 1 by n plus 23 plus 0.00155 by s divided by 1 plus 23 plus 0.00155 by s into n by root r. N by root r into under root rs. I know this expression is very difficult to learn, but we have to learn. Okay, so just keep revising this formula or this coefficient every time you solve this numerical, and within 2 or 3 revisions I think you will be able to learn you'll learn this formula. Okay, so n is the Cutter's rugosity coefficient. Okay, n is the Cutter's rugosity coefficient, and in the question we have been already given this value to be 0.023. Cutter's rugosity coefficient 0.023. So we need not to, we have this value. Okay, hydraulic mean depth we have already found in the previous steps. The bed slope in this question we have been given the bed slope as 1 by 4000. Okay, we have been given the bed slope as 1 by 4000. If this value was not given, then again we have to assume the bed slope based upon the guidelines that we have discussed in the previous lecture. Okay, these are those guidelines. You can assume any value as per your own desire. Okay, so to find out the actual velocity, let's just put the values here. Put the values here. We have 1 divided by 0.023 plus 23 plus 0.00155 divided by s. Best slope we have been given in the question, so it will be 1 by 4000. 1 by 4000. Okay, divided by 1 plus 23 plus 0.00155 divided by 1 by 4000. N, what is the value of n? 0.023 divided by under root of r. The value of r is 1.77 meter. The value of r is 1.77 meters. So this is this into under root rs. R 1.77 s 1 by 4000. Okay, now solve this value. Okay, solve this value and see what is the answer that you are getting. See, this is the trickiest part of this whole Kennedy's theory. If you are getting this value right, then there is nothing to worry about in Kennedy's theory. Okay, and generally this value comes out around 48.01 to 48.08. Like this is the range in which the value will come. Okay, generally it comes around 48.30. It comes around like 48.30, 48.6, 48.6. This is the the range in which it comes. So, but like the value will be 48, it will be around 48. Okay, 48 something. So this is a parameter through which you can check the if your calculation is correct or not. If it is not coming around 48 something, then redo the calculations. Okay, this is just a guideline that I can give it to you. Okay, so if you solve here, this value will come out to be 48.30. The value will come out to be 48.30. Just check if you are getting this value. If you're getting around 48 point something, if you're getting 14.6 or like that, again, it's within the acceptable range. Okay, so then 1.77 into 1 by 4000. This is the actual velocity. Now solving this, the actual velocity value will come out to be around 1.016 meter per second. Okay, this is the actual value that we are getting. What was the critical value that we got? The critical value, the critical velocity that we got, was 0.942 meter per second. So if you look here, our V is 1.016, V naught is 0.942 meter per second. Always remember to write the units. Okay. Now definitely our V is not equal to V naught. Our V, the actual velocity, is not equal to our critical velocity that we have got by considering a trial depth. Hence, we have to repeat these steps. We have no option but to repeat the design steps. You have to repeat the design steps. We have to repeat the design steps. Now, since our actual velocity is greater than the critical velocity, and in the formula V naught is equals to 0.55 m y to the power 0.64. So the critical velocity is directly related to the trial depth. Our critical velocity is directly related to the trial depth y. So here in this case we want to increase our critical velocity, correct? So definitely we have to increase the depth. We have to increase the depth. Hence increase the depth. Increase the depth. And then we have to again go to step one by considering a new trial depth. Now Again, so see, the first trial depth that we have considered was 2 meters. So now if we can consider it to be 3 meters, and then again we can redo the question. Now, I'm not going to again repeat the question, but if we consider y equals to 3 meter, our actual velocity and critical velocity, the critical velocity will come out to be around 1.22 meter per second, and our actual velocity will come out to be around 1.16 meter per second. Okay, now like discussed in the previous lecture, we want up to two decimal places, at least the value should match. Okay, this is like the general our aim. If you see here, or our actual velocity is less than the V naught. Our actual velocity in this case, if we do that, will be less than V naught. Now, what we want? We want our V naught in the next iteration. This is at taking y equals to 3 will be iteration 2. This will be iteration 2. So in the iteration 3, in the iteration 3, in iteration 2, what we are getting? We are basically our critical velocity is higher, and now we want to decrease this velocity. So to that, what we are going to do? We are going to decrease the value of new trial depth. So here to do so, so that we know it is in between 2 to 3. So we can take 2.5. Okay, so if you take y equals to 2.5, you will again get a new value, right? And then the new value at y equal to 2.5, I know the values just to avoid these reiterations and same things again and again. I'm just writing the value. The V naught will come out to be around 1.087 meter per second, and the actual velocity will come out to be 1.1 meter per second. It will come out to be around 1.1 meter per second. Now here, if you see, our actual velocity is greater than critical velocity. So again, what we need to do? We need to increase the trial depth. We need to increase the trial depth. So in iteration 4, you can take a trial depth of 2.7 meter. You can take a trial depth of 2.7 meter, and at a trial depth of 2.7 meter, the V naught value will come out to be 1.147, and the actual value will come out to be around 1.148 meter per second. And you can see here these are matching up to two decimal places, so this is the depth that will come. Okay, so what I want you to do is you do repeat the design step, taking a depth of y equal to 3, y equal to 2.5, and y equal to 2.7. Repeat the same step that we have discussed in this video using these using the step that we have discussed. Okay, and then see if you are getting the value correctly or not. If you have any doubt, you can always ask in the comment section. I hope the lecture was clear to you. Okay, but still there can always be some doubt, some confusion. So if that is the case, then you can always ask in the comment section. There is another type of question for candy theory in which we are given the width to depth ratio, and in such cases the methodology that we have to adopt is there's a slight change in that, because since we are given now the overall aspect ratio, so we have to adhere to that, and then considering this we have to design the regime channel. That question we are going to discuss in the next video lecture. So do subscribe to the channel and press the bell icon for the notification as and when the lecture is uploaded. Okay, so that's it for this video. Thank you for watching. Have a nice day.